here. Okay. All right. Now, question number 8. It reads as follows. It says to us, two reactions of sulfuric acids of acid are shown in the diagram below. So we have reaction number 1 and we have reaction number 2. We have sulfuric acid. In reaction number 1, sulfuric acid, it is reacting with sodium hydroxide. You know what? Let me write it in this way because this maybe it might confuse you a little bit. So for reaction number 1, we can see that we have the sulfuric acid reacting with sodium hydroxide to form what you call a salt and a product Y. So here we have X and then there we have Y, okay? It's a reaction of an acid and a base to form a salt and product Y. All the times when acid and base react together, one of the products supposed to be water. For a fact that here we have salt, we are certain that we know that salt will depend on acid and base that has reacted. But product Y, for a fact that product Y is not salt, that means it is water. So that means water will most definitely come here. And the salt, remember, sulfuric acid in this chemical reaction, it is regarded to be a diprotic acid. A diprotic acid, it is acid that can donate hydrogen 2 times. How do we see that this is a diprotic acid? By these 2 over here. So that means we can donate our proton 2 times. In this case, for first reaction, acid will donate only 1 proton and therefore or you can donate two protons. You'll see. I think you do that in grade 12, or also in grade 11 diprotic acid, but it's fine. So in this case, this hydrogen and this OH, they're gonna combine together to form water, and therefore our salt will be combination of sodium and SO4 2 minus ion. So that means our salt in this case will be Na open bracket. Sulfate. Let me write it this way. Sulfate, it is SO4 2 minus ions, okay? So that means you're going to have Na2SO4. This will be our salt. And in reaction number 2, we can see that, again, our sulfuric acid, which is H2SO4. In this case, our sulfuric acid will react with water, now. An N4-lite. Remember, what is an N4-lite? So in this case, we have an N4-lite A that's going to be formed and oxonium ions or hydronium ions. So we know that in this case, for a fact that this is the acid, will donate its proton to water, and therefore water will turn into hydronium ions. But what is this N4-lite that it is going to be formed? An N4-lite, now this is a diprotic acid. If this donates only once, so that means you're gonna have HSO4 minus. Why do I write minus over here? To show that this acid has donated only 1 proton and it is left with 1 proton. Remember, we had 2 hydrogen atoms, but because you're going to donate only 1, we're going to left with 1 over there. So this minus is an indication that shows that H2SO4 has lost 1 proton to water, and therefore this, it is regarded as an N4-lite. Why is it regarded as an N4-lite? Because something that looks like this, it can add, it can accept a proton to form something like this, or it can donate a proton to have SO4 minus ion. If we donate this proton, it's going to be SO4 2 minus ion. Okay, so this is an N4-lite, can act as either acid or a base. That's why they say N4-lite A. Now, let us try to answer the questions. So 8.1.1, they say to us, define a Lorry-Bousted base. You see, they love asking this question. So also make note of your Arrhenius theory. So Lorry-Bousted base, not Lorry-Bousted acid. So it is a proton acceptor. It is a proton acceptor. Okay. All right. Now 8.1.2, they say to us, write down a balanced equation for R1. Write down the balanced equation for R1. We have already written the reaction over there for reaction number 1, but let's make sure that the equation, it is most definitely balanced for 3 marks. So in this chemical reaction, we can see that here we have 2 hydrogen atoms. We have 3 when you add them. So how many number of hydrogen atoms do we have on this side of the equation? It's 3. So on this side of the equation, we have only 2 hydrogen atoms. So that means we're going to need how many number of hydrogen atoms? We're going to multiply this by 3 so that we can have now 6. Now let's go back. On this side of the equation, now we have 3 hydrogen atoms, and then now we have 6 hydrogen atoms instead of 3. So we need to change number of hydrogen atoms. So in order for us to change number of hydrogen atoms, we can add, let me see, did we write the correct equation here? If we add 2 over here, we have 6, right? 2 multiplied by 2, it's going to be that. Okay, if we add 2 over here, because I'm looking at an A, we're going to need 2. So I don't want to go higher. So if we add 2 over here, it's going to be 2 multiplied by 1. It's going to be 2. And then here we're going to be 2. We're still short of hydrogens because there we have 6. So if I write 2 over here, I'm going to have 4 hydrogen atoms plus these 2 hydrogen atoms. Now I have 6 hydrogen atoms. And this side I have 6 hydrogen atoms. Now let's talk about the sulfur. How many sulfur do we have on this side of the equation? Let me confirm this. Wait, how many sulfur? I think, let me confirm this first. What is it? NOH, I get it. And then we have water and also 2. Let's try to confirm this. So we had this initially, right? This side is going to be, let me see, we have 2 hydrogen atoms, we have 3 hydrogen atoms, and then we have that, which is H2, is going to be 6. Okay, sharp, fine, all right? Now, let us try to balance the sulfur. Sulfur, it's 2 hydrogen atoms, and this side, we only have 1. So we're going to have to add 2 there so that they can be 2. But now we have affected the oxygen atoms. You see? Now let us rebalance the oxygen atoms. So now in this side of the equation is going to be 2 multiplied by 4. It is 8. And therefore, 2 multiplied by 4, it is 8. And therefore, 2 multiplied by 2, it is 2. 8 plus 2, it's 10. Now let's go this side of the equation. So we're going to have 2 multiplied by 4, it's going to be 8. And then 3 multiplied by 1, it's going to be how much? It's going to be 3. 3 plus 8 is going to be 9. Let me check this. Wait. Let me try to confirm this. Oh, I did this. I was supposed to do this. Oh, I was supposed to add 2 there, not 3. Let me do this. Let us try to rebalance it once more again. Let's start again to balance our equation. So now, hydrogen, we have 2 plus 1. It's going to be 3 hydrogen atoms on this side of the equation. And therefore, here we have how many hydrogen atoms? We have 2, right? We have 2. So I'm going to multiply this by 2. 2 multiplied by 2 is going to be 4. So remember, here I have 3. So I'm going to multiply this by 2 so that I can have 2 hydrogen atoms. 2 multiplied by 2, it's 2. And therefore, plus this 2 is going to be 4. Now the hydrogen atoms are balanced. We have 4 hydrogen atoms. We have 4 hydrogen atoms on this side of the equation. Now let's talk about sulfur. Sulfur, we have only one sulfur atom on this side of the equation, and on this side of the equation we have only one sulfur. It is balanced. Now let's go to oxygen. Oxygen, we have 4 plus, remember here it's going to be 2 multiplied by 1. So 2 multiplied by 1 is 2. 2 plus this 4 is going to give us 6. We have 6 hydrogen atoms on the oxygen atoms on this side. And therefore, how many oxygen atoms do we have here? We have 4. And then 2 multiplied by 1, it's going to be 2. And then 2 plus 4 is going to be 6. Now oxygen atoms are balanced. Now let's have a look at sodium. We have 2 sodium and then we have 2 sodium. Everything it is now balanced. So that means to answer question number 8.1.2, we're just going to refer to this, what I wrote over there, which is a balanced chemical equation now. This will answer this question. Now 8.1.3. It says to us, write down the name of the salt presented by X. The name, listen, not the formula, the name. What is the name of this salt presented by X? It is sodium sulfate, okay? We have sodium sulfate. That will be our salt presented by X. Now, 8.1.4, it says to us, write down the formula of N-folate A. Formula of N-folate A, I have already written it over there. I have shown you how was this formed. So that means it's going to be HSO4 minus ions. Okay, that's an N-folate A, which is this over there. Sorry, and then 8.1.5, it says to us, write down the formulae of 2 conjugate acid-base pair in reaction number 2. So they want 2 of them. So reaction number 2, I'm going to take reaction number 2 from here. So reaction number 2, check. This thing has turned into this thing. This thing has turned into that thing. These are the conjugate base pairs, right? So now this is what I'm going to do. This is very simple. These are conjugate base pairs. This is the conjugate of this one, and then these are the conjugate base pairs. So that means we're going to say it's H2SO4 and HSO4 minus ions. Another pair, it is this one. This for 4 marks. This for 2 marks and 2 marks for the other one. So another one is going to be H2O and H3O plus ions. So you get your 4 marks from this computation. So they just wanted you to write down the formulae of 2 conjugate. These are 2, 1, 2. These are 2 conjugate acid base pairs. Now we move to question number 8.5, calculations. 8.2, sorry, 8.2. 8.2, it says from the theoretical questions, a solution of sodium hydroxide is prepared by dissolving 6 grams solid of sodium hydroxide in 500 cubic centimeter of water. So this is what is happening. Let's say we have a beaker. Now we have water in this beaker. And the volume, remember, I don't want this. What I do, I divide by 1,000. I hate it with all my heart because it's cubic centimeters. So that means I divide by 1,000 and then we get 0.5. So that means here we have 0.5 cubic decimeters. So they say to us, the volume of water, it's volume of water in this case, it's 0.5 cubic decimeter. So we're gonna take sodium hydroxide, the solid in a form of solid, right? This is a solid of sodium hydroxide. I'm just making an example. So it is 6 grams. The mass of this sodium hydroxide in a solid form It is 6 grams. So we're going to weigh this in water. Now, a solution will be prepared. A solution will be prepared. That means in this case, we're going to have a volume of 0.5 cubic decimeter. And inside of this, we're going to have we're going to have number of moles, we're going to have concentration, we're going to have solution. That means we're going to have a solution. Solution of what? Solution of sodium hydroxide and water. We prepare that solution in this beaker, right? Right. So they say to us, after preparing this solution, what is happening? This solution reacts completely with 10 grams. That means in this solution, we're going to add 10 grams of what? Let's hear. The solution reacts completely meaning it's a limiting reagent. The solution reacts completely with 10 grams in pure ammonium chloride. So we're gonna add 10 grams of impure ammonium chloride, which is NH4Cl, in this solution of sodium hydroxide. According to the equation, this is the reaction that's going to take place inside of this beaker. So that means sodium hydroxide will react with this ammonium chloride to form this and that and that. Now they say to us, the equation is balanced. Make sure that the equation is balanced. The Na11, OH, oxygens are balanced. H, we have 5 this side. We also have 5 this side, H's. N it's 1, and it's, what is N? N is 1. Yeah, the equation is balanced. Now they say to us, calculate the concentration of sodium hydroxide solution. We want concentration of this, of sodium. This is, remember, we prepared it over here. So we want concentration before we can add 10 grams of what? We want to calculate the concentration of sodium hydroxide by itself. So for sodium hydroxide, we are given mass, we are given the volume, and we want to calculate its concentration. So to answer question number 8.2.1, to calculate concentration, we know that we use this formula that says N over V. The thing is, in order for us to determine the concentration of sodium hydroxide, we have volume, which is 0.5. But we do not have number of moles. Instead, we have mass. So we know that we have a formula that we use to convert mass into number of moles. That formula, it is given by number of moles is equals to mass over molar mass. So, because I do not have number of moles, I'm going to substitute number of moles. This equation, I'm going to substitute it over there. So that means C is the same as, or you can just determine mass aside, it is still fine. So that means we're going to say mass over molar mass. This is the same as moles, right? This number of moles, right? Multiply by 1 over V. So that means we can use this formula quickly. Here we have molar mass, and then here we're going to multiply by V. We can quickly use this formula to determine the concentration of sodium hydroxide. So what is the mass of sodium hydroxide? It is 6 grams. And then molar mass of sodium hydroxide from the periodic table, Na, the molar mass of Na in this case is going to be how much? I think it's 23. Yes, you're going to say 23 plus of oxygen, it's of oxygen, sodium hydroxide. Of oxygen, it's 16, and hydrogen, it's 1. And we close the bracket. And then what is the volume? Volume is 0.5 cubic decimeters. Now let us determine the concentration on our calculator. Fraction 6 divide by 23 plus 16 plus 1 multiply by 0.5. And therefore, we get 0.3. We get 0.3 moles per cubic decimeters. Now, this is the concentration of sodium hydroxide. We use the mass of sodium hydroxide, the molar mass, and the volume of sodium hydroxide in that solution. Therefore, this is how sodium hydroxide is concentrated in that water. Now, we move to 8.22. Now 8.22, it says to us, calculate the percentage impurities in H4Cl for 6 marks. How I love to calculate this is I calculate percentage purity first. Okay, I'll show you how. Let me do this. Now we want to calculate the percentage purity of this thing. Here's the thing, right? Remember, according to this chemical equation, sodium hydroxide will react with impure NH4Cl. What does impure mean? It means NH4Cl, it is not only, like, for an example, if you have a sample, a large sample, that large sample, it has what you want inside of it. That means it is impure because it has extra chemicals with it. So NH4Cl, it is impure because it has other elements that we are not interested onto. So we're going to take that impure sample. So remember this impure sample, remember the solution reacts completely with 10 grams of impure ammonium hydroxide, meaning this 10 grams, it is not 10 grams for, and it is not the 10 grams for this thing. Where is it? It is not 10 grams for NH4Cl. This 10 grams, there's combination of other elements. That's why we say it is impure. Ne? Right. It is 10 grams. So now this is what we're going to do. We're going to determine exact mass. We're going to determine pure mass of this. Okay, we're going to determine pure mass of NH4Cl that is going to react with sodium hydroxide according to this equation. And remember, sodium hydroxide, it completely reacts, meaning it is your limiting reagent. So from this equation, let's determine number of moles of sodium hydroxide. 8.2.2. We have already determined concentration, blah, blah, blah. We didn't determine number of moles. So we can determine number of moles using this equation. So to determine number of moles of sodium hydroxide, we're going to use mass over molar mass. Mass of sodium hydroxide, remember we said it's 6 grams. And then the molar mass, I didn't calculate it, but I said it's 23. It's 23 plus 16 plus 1. So that means it's going to be 23 plus 16 plus 1. And therefore, when we punch this on our calculator, we're going to say 6 divided by 23 plus 16 plus 1. And then we get 0.15 moles. Sorry. For the fact that sodium hydroxide is our limiting reagent, it will help us to determine number of moles of NH4Cl, ammonium chloride. So, from the balanced chemical equation, we have 1 mole of NaOH, and then we have 1 mole of NaCl. But I'm not going to do that ratio. Why? Because 1 mole, 1 mole. So that means the number of moles of NH4Cl will be the same as number of moles of sodium hydroxide, NaOH. You can do that ratio. According to 1 mole of NaOH is to 1 mole of, you can do that, but it's unnecessary because this is 1, 1. If it was 2, I was going to do it. But because I have 1, 1, I can just say, oh, that means this calculated number of moles is going to be the same as this number of moles. You understand? So that means number of moles of NH4Cl will also be 0.15 moles. Now, let us determine the reacted mass of this thing, pure reacted mass of NH4Cl. So we're going to say mass is equals to number of moles multiplied by molar mass. So number of moles of NH4Cl, it's 0.15. And then for the molar mass, remember it's nitrogen. Nitrogen, I think it's 14, right? Yeah, nitrogen is 14. So we have 14 plus hydrogen, we have 4 hydrogens. So it's going to be 4 multiplied by 1 plus, remember we calculating molar mass. Aluminum, chlorine, I think is 35.5. It's 35.5. So here we're going to have 35.5. and then we close our bracket. So now let us do calculations. So you're gonna say 0.15, open bracket, my answer, open bracket, 14 plus 4, because 4 multiplied by 1 is 4, plus 35.5. And therefore I get my answer to be mass of this thing. Where is it? Mass of this NH4. Let me say it's gonna be 8,025 grams. So this is mass of NH4 Cl. This is the mass of NH4Cl, a pure mass that is going to react with sodium hydroxide. You see, not 10 grams. So where is the remaining mass? Because you're going to say 10 grams minus this. The remaining mass is for other substances. Because remember, NH4Cl, it is impure in this case. You understand? All right. So now let us determine percentage purity because we have pure mass. So we're going to say percentage purity is equals to mass of what? We're going to say mass of our pure over, we're going to say, let me write the formula. Mass of pure substance divide by mass of impure substance multiply by 100. So now what is the mass of pure substance in this case? This is the substance of interest, NH4Cl. It's 8,025 grams. Divide, what is the mass of impure substance of NH? They said it's 10 grams. It was provided. It is 10 grams. Multiply by 100. So now, when you punch this on our calculator, we're going to say 8,025 divide by 10. And then how much is it? Multiply by 100. And to 2 decimal place, it's already in 2 decimal place. We're going to get 80,25%. So this is the percentage purity. This is the percentage purity. We are not looking for percentage purity. Rather, we are looking for percentage impurity. So all the time, again, another formula is that a percentage impurity is gonna be 100% subtract percentage purity, right? Subtract percentage purity. In this case, we're gonna say 100% subtract 80,25%, and therefore our percentage impurity, we just minus 100 on the answer, which is gonna be 19,75%, and therefore this will be our final answer.